All right, so we're going to go beyond Hess's law and see how it's actually a lot of times easier if you have exactly the right type of tabulated data that can make this sort of guesswork that you see in Hess's law simpler. So the main learning objective this time is to understand what standard enthalpies of formation are. These are enthalpies of reaction, but enthalpies of very specific reactions that make the bookkeeping much easier, and calculate the enthalpy of reactions using these heats of formation. Enthalpies of formation, heats of formation are essentially used interchangeably. Okay, so the enthalpy change, now we have delta H standard state F for the formation of 1 mole of a substance in its standard state, again at 25 degrees C, 1 atmospheres, from its constituent elements in their standard states. So for example, the heat of formation of calcium solid is 0 kilojoules per mole. Whereas for calcium in its gas phase, that's not very favorable. The heat of formation is 177.8 kilojoules per mole. It takes a lot of heat to be put in to get that. Why do we choose standard states with the solids? It's just more convenient. We have to pick a standard state, so that's a convenient place to go from. Remember, what we're interested in changes of enthalpy is not the absolute enthalpy. So we can set any references we want. We just have to set a convenient one that's easy to work with, because what we're interested in reactions is how the enthalpy changes. So let's take a look at a few enthalpies of formation. Here we have carbon. Remember, carbon at 25 degrees C, its most stable state is just solid carbon, graphite. H2 gas, producing acetylene gas. So that heat of formation is 227.4 kilojoules per mole. We can look at the, again, the enthalpy of formation of ethylene, the same. We have each of the elements in their same most stable states. You get that heat formation, and then finally the reaction to ethane. So those are 3 different heats of formation. Notice a heat of formation is a heat of reaction. It's just the heat of a very specific reaction of combining all the elements together to make that compound. So, so the formula for calculating a heat of reaction using a heat of formation is this. It's the sum of the heats of formation of the products minus the sum of the heats of formation of the reactant. The final ones minus the product minus the initial. But really, this is just Hess's law with a special set of reactions. This magical reaction where we take the reactants and rip them apart into their constituent elements of their most stable state, and then combine them, and so that would be minus the heat of formations, because we're tearing apart all the reactants, and then we're reassembling them into their products. And so those reactions, that's the sum of each of the compounds, the sum of the heat of formation of each of those compounds. So it's just this sequence of reactions, which would very rarely happen in real life, but it doesn't matter because enthalpy is a state function. We can construct any arbitrary path from reactants to products. So that's what we care about. So we construct this magical cycle, which you do throughout chemistry and chemical engineering and any other engineering. For any state function, you calculate your convenient path. Thermodynamics, mechanical engineering, thermodynamics, this happens a lot as well. You construct a cycle that's easy to calculate, but it gets you to the reaction you actually care about, even if you can't calculate that. So that is the key. This formula is just Hess's law. That's how you can remember it. The sum of the heats of the formation of the products, the final state, minus the sum of the heats of formation of the reactants. Yeah, that's what we care about. So let's take a look at this. Let's look at an example. So let's say we're interested in this reaction of NO plus NO2 plus oxygen to produce N2O4. And we're given these heats of formation. Let's check to make sure they are heats of formation. Yes, they all involve on one side nitrogen, just nitrogen and oxygen in their most stable states. And on the right side, we have just the compound. Notice you've got 1/2, you've got 1/2 here on the nitrogen, but that's just because the stoichiometry has to work out such that it is the actual compound on this side. So this has 2 nitrogens, so there we have the full nitrogen gas. Here we have, on the other ones, we have 1/2 nitrogens because it has to have only 1 nitrogen in the compound. Okay, so this is what we've got. So all we need to do is plug into the formula. It's pretty straightforward at this point, which is much easier than Hess's law when you have to go through, jump all these hoops to find exactly how they fit together. When I say this is Hess's law too, but instead of a Hess's law problem, when you're given equations that are not pre-derived in simple form to make it easy to have a formula that you can use every time rather than piecing it together. So we have delta H reaction, standard state, because heats of formation are at standard state. So when we plug these into the formula, we're going to get something that's at a standard state reaction too. So in this case, the product, there's just one product. It's going to be delta H of formation of N2O4 minus the sum of the heats of formation of the products, which is delta heat of formation of NO plus heat of formation of NO2 plus 1/2 the heat of formation of O2. All right, and so this we can just look up. This is 11 kilojoules per mole minus 91 plus 33. Oh, oxygen. I don't have the heat of formation of oxygen. What do I do? Well, the heat of formation of any compound in its stable state is just going to be 0. So that'll be 0. And so this all adds together. We get 11 minus 113, which, 11 plus 11 minus 124, which gives us minus 113 kilojoules per mole. So a process that was a little complicated using just random heats of reaction, we can make something much more consistent. We only have to tabulate one set of heats of formation. One thing you might ask is, well, what about heats of formation of reactions that are very hard to measure? It turns out the way they usually do that is use Hess's law to back calculate the heats of formation using reactions that are easy to do. So you do, to get these heats of formation, frequently you do have to use Hess's law with random reactions that you can stack together. But once you do that, then using heats of formation is the way to tabulate all that thermochemical information in a way that can be handled easily and concisely. So that is how we simplify Hess's law and just use heats of formation to calculate our heats of reaction.